Hello and welcome friends. In our previous lectures, we have been discussing dynamic programming, which is one of the algorithmic techniques of solving certain computational problems. In dynamic programming, we used a divide and conquer approach that we were already familiar with. However, we modified it to use memoization. And by doing so, we somehow reduced the number of computations that we had to perform by simply eliminating the need for recomputing solutions for overlapping problems. That's how basically we tried to reduce the number of computations in case of dynamic programming. Now from today onwards, for a couple of lectures, we will be discussing another technique for solving computational problems, and this technique is known as backtracking. And what is backtracking basically? The simple definition of backtracking is that it is a general algorithmic technique that considers searching every possible combination in order to solve a computational problem. So what does that basically mean? It means, let's suppose we consider an example of a problem wherein the solution to the problem can be obtained by following a certain number of steps, and at each step we have different choices. We can take any particular path. So using backtracking, we can try to find a solution for such a problem by considering every choice that is available at that particular step, and then trying to find a solution by following all possible paths. However, it is not always computationally efficient because the number of possibilities for a certain problem, for a certain computational problem, might be exponentially large. So backtracking, it tries to build a solution incrementally, one piece at a time, so one step at a time, and it tries to remove those solutions that fail to satisfy certain constraints that are imposed on the problem at any point of time. While finding the solution at any particular step, if we find that at this particular step a particular choice may not lead to an optimal solution, then we'll simply stop expanding the other possibilities that follow from that particular point of time. It will be more clear if we take a simple example. There are two batsmen in a cricket match and they have to score 18 runs in the last 5 balls of the match. Now, however, the batsman cannot depend on luck, on overthrows, on wide balls, on no balls, and there are certain constraints imposed on the way the batsman can score these runs. Now, the constraints, as you can see on the slide there, one of the constraints is that it is predicted that the bowler will bowl ball numbers 2 and 4 as Yorkers. So it is predicted, depending upon his analysis, the analysis that has been performed on the bowler, it's expected that he will bowl ball number 2 and ball number 4 as Yorkers, and the batsman will not be able to score more than 1 run on those 2 balls. In addition to these constraints, the other constraints imposed on the batsman is that any ball except for the second and the fourth ball, they can either rotate the strike, means they can get a single, or hit a boundary or a 6. So these are the constraints under which the batsmen have to score 18 runs of the last 5 balls of the match to win. So the problem with us is to find the number of ways that these batsmen can score at each of these balls to win the match. So what will be the sequence of scoring runs at each of these 5 balls, provided we follow these constraints. So let's try to formulate this problem in a mathematical way. The formulation of the same problem, as you can see on the slide, let's consider S1 would be the score scored for ball number 1, S2 would be the score scored for ball number 2, S3 for ball number 3, S4 for ball number 4, and S5 ball number 5. So the basic objective at hand in this case is that the sum of these 5 scores that the batsman will score at each of these 5 balls has to be greater than or equal to 18. That is the required number of runs to win the match. And subject to the constraint that the score at ball number 1, as you can see on the slide, score at ball number 3 and ball number 5 can take values only from 1, 4 and 6. And also the score at ball number 2 and ball number 4 can only be 1 because they will be Yorkers. Yes, you might kind of consider that there could be sheer luck that batsman might get runs from no ball, from wide balls, and so on and so forth. But for the time being, we are not considering all those possibilities. So we are sticking to the constraints that have been specified in the problem, and the requirement, the objective is to score 18 runs. So based on this formulation, we'll try to find all the possibilities by which the two batsmen can score runs in these 5 balls. And we might represent all those possibilities using a state space tree that is often used in backtracking and branch and bound later. But for the time being, we'll consider the state space tree as one of the representations used to show the possible solutions to a particular computational problem. Starting from an initial score, the possibility for the batsman on strike is that he might score a single for the first ball, so S1 is equal to 1. Similarly, the other possibilities, he might score a 4 or a 6. So these are the 3 possibilities based on the constraints that have been imposed in the problem. So these are the only ways the batsman at strike can score from this first ball. Now the second ball, as I said, according to the constraint, has to be a Yorker ball, and the batsman on strike can only score a single run. So following any of these possibilities in the first ball, the second ball can only yield a single run. And the values on the nodes here represent the number of runs that have been scored so far. So if you follow this path here, so for the first 2 balls we have scored 2 runs. Similarly, if you follow this path here, we have scored 5 runs. Similarly, if you follow this path, it means that we have scored 7 runs. Similarly, the other possibility in the third ball would be that we can score a single or hit a 4 or a 6. So these 3 choices can be made at each of these 3 leaf nodes in the tree. So this is the possibility that we can have. So after the first ball, we have, for example, let's suppose scored a single, then we hit another single, then we can hit a single again. Similarly, we hit a single the first ball, second ball we hit another single, and then we can hit a 4. Similarly, the third ball we can hit a 6. Or we can have these other options. For example, we might score a 4, after that we might score a single, then we can score another single, or a 4 or a 6. Or alternatively, in the first ball the batsman hit a 6, then score a single, then they can score another single, or they might hit a 4 or a 6, and so on and so forth. And finally, as you can see on the screen here, the final ball, when considering the final ball, it will yield all these possibilities as are shown on the screen. Now we have restricted, as I said, we have restricted ourselves to the constraints only specified in the problem. Otherwise, the state space tree, if we consider all possibilities, a wide ball, a no ball, a leg by, similarly an overthrow of 3 or 4 runs, if we had considered all those possibilities, then the state space tree would have been very, very large. Okay, but sticking to the constraints, this is the size of the tree that we were able to build. So what this state space tree basically means is, as I have already told you, a path from this root node here to any other node in the state space tree, usually, for example, a leaf node. So each path from a root to any particular node in this state space tree gives a possible solution vector to the problem. So we need to find out which of these vectors is a feasible solution to the problem. For example, if we look at this path here highlighted on the slide, we hit a single in the first ball, so the score is 1. Similarly, we hit the single in the second ball, so score is 2. Similarly, in the third ball, we hit a 6, so the total score is 8. In the fourth, we hit a single, so the total score is 9. And in the fifth ball, we hit a 6, and the total score is 15. So in this case, we have exhausted all the 5 balls, but the total score here, or the required score, okay, is not equal to or greater than 18. So this is not a valid or a feasible or an optimal solution to our problem. On the other hand, if we consider this second path on the extreme right of this tree here, we follow this path. So we hit a 6 in the first ball, hit a single in the second ball, hit a 6 in the third ball, hit a single in the fourth ball, and finally hit a 6 in the fifth ball, and the resulting score is 20, which is greater than or equal to 18. So this is a possible solution vector for our problem. S1 is equal to 6, S2 is equal to 1, S3 is equal to 6, S4 is equal to 1, and S5 is equal to 6. And that is what is shown in this current slide, all possible or feasible solutions to the given problem. The nodes marked in orange are basically the leaf nodes to which a path from the root yields a feasible solution to the given problem, because the total score that we are able to get at the end of this vector is greater than or equal to 18. So this problem is just an example of seeing what a state space tree is and what are the possible solutions. However, backtracking tries to minimize the number of nodes in the state space tree that it needs to search. So it tries to minimize. How? By somehow bounding or somehow stopping the expansion of a node. For example, if we look at this statement in the next slide, it says that creating a complete state space tree and then searching for the solution or solutions, if there are multiple, at the leaf nodes is not a feasible solution. For example, in certain cases, when the problem is large, the state space tree might be extremely huge, and it would be difficult for us to kind of find an optimal way of searching that huge state space tree. So alternatively, we can use backtracking. Now, how does backtracking kind of give us a better solution? It involves constructing only a partial state space tree. So how does it do that? How does it create only a partial state space tree? Or it tries to build the solution vector one component at a time, and while it is building this solution one component at a time, if it finds or realizes that this partial vector up to which it has reached, for example, in our previous example, this path here is a partial vector. So ball number 1 and ball number 2 we have found, or this is one of the possibilities that we can follow. And at ball number 3 we have a choice 1 or 4 or 6. Okay. So at this particular stage we can easily see that if we follow this path here, means if we score a 6 in the first ball, hit a single in the second ball and hit a single in the third ball, then none of the leaf nodes or none of the intermediate nodes after this particular shot yields a feasible solution. So we can simply discard building the state space or searching the nodes after this particular node. Same applies to, for example, this node. If we hit a single in the first ball of these 5 balls, then in no way can we reach, if you look at this state space tree here, okay, this subtree, none of the nodes here yields a feasible solution. So we can simply omit this or start or not expand or search other nodes after this particular node. Okay. So that is what backtracking basically tries to do. If we realize that a partial vector, the partial solution that we have constructed so far does not yield or cannot lead to an optimal solution, okay, then many possible vectors can simply be ignored by not following or searching the state space tree. Now, as I've shown in the slide here, these are some of the nodes where it is very clear that following further searches for these nodes, the nodes marked as red. So once we have reached these red nodes, it is obviously clear that we will not keep on searching the state space tree onwards from this red node onwards. We will not be able to find an optimal solution. Now, same applies to this node. This subtree does not yield any optimal solution. Same applies to this node. This subtree does not yield an optimal solution. Same applies to this node as well. Okay. So the simplest solution would be somehow that backtracking should not allow us expansion or searching these subtrees which basically do not yield a possible solution. So the partial state space tree that should be yielded by backtracking as per our definition that we said is the one that is shown in the slide here. You can see we have omitted a large number of possible vectors which otherwise we would have to search, but backtracking tries to somehow reduce our searches by stopping us at certain point of time. Okay. So we'll see later on in a more standard example, although this example that we talked about is not a standard one, but it is useful for making you understand the basic concept of backtracking, a state space tree, and how basically we can bind our solutions or stop expansion. The question is that which problems can be solved using backtracking. Okay. So on the slide you can see that generally every constraint satisfaction problem which has clear and well-defined constraints on any objective solution can be solved by backtracking. So you have an objective function which either you need to maximize or minimize subject to certain constraints. Provided we are able to incrementally build solution to this particular problem, and upon traversing each of these elements, we are able to abandon certain candidates, which basically means backtracking to a previous decision. As soon as we determine that a candidate cannot possibly be completed to a valid solution. So as soon as we determine that if we follow this particular node to the leaf nodes, we might not be able to get a valid solution. So we simply try to backtrack at that point and not follow the state space tree to find the solution. And there are a couple of problems which basically have these properties. For example, decision problems, wherein we basically search for a feasible solution. Optimization problems, wherein we search for the best solution. Similarly, enumeration problems, when we need to find all possible or all feasible solutions. In the decision problem, there might be a single solution to the problem, okay, a single feasible solution. But in enumeration problems, there could be more than one feasible solutions, and we need to find all such solutions to the problem. Now, the general formulation of backtracking is that, as we'll use the previous example to illustrate this formulation. Now, let's suppose we have a partial solution vector S1, S2 and up to Si, as can be seen in the slide. Let's suppose this is a path from the root to any node in the state space tree. Now, in the example here, in our previous example, let's suppose this partial vector is this S1 shown in green, okay. So S1 is equal to 6 and S2 is equal to 1. So this is a partial path from root to any node in the state space tree. Now, let's suppose this T of this partial vector as statement here. Now, let this represent the set of all possible values for which Si plus 1. So, if we are considering Si to be the choice for step number I, okay. Now, Si plus 1 is the choice for step I plus 1, okay. So, we are trying, this T here represents all possible choices that can be made for Si plus 1, such that this S1, S2, Si and Si plus 1 are also a path to the problem state, okay. Now, in our example, if we can see is, since this partial path is S1 is equal to 6 and S2 is equal to 1. So, based on the previous statement, T of 6 comma 1 is simply the set, it is 1 means S3 here. So, Si plus 1 is, we are considering I to be equal to 2 here, okay, and Si plus 1 is S3, okay. So, the possibilities for S3 are 1, 4 and 6. So, this T of 6 comma 1 is equal to 1, 4 and 6, okay. So, these are the values that will be returned by this function here. So, let T of S1, S2, Si be the set of all possible values for Si plus 1 in the next step, such that S1, S2 and Si plus 1 are also a path to the problem state, okay, or also a path in the state space tree. It is obvious for the path from the first node to the last node here meaning that you have exhausted all the steps, okay. So, T of such a path is simply equal to phi. Phi here means we have no other choice to make. So, we have exhausted all our options. In this example here, let us consider this path. So, S1, S2, S3, S4 and S5, okay. So, T of 4 comma 1 comma 6, this 6, this 1 and this final 6 is simply is equal to phi, because we do not have any other choice to be followed in this case, okay. So, we are trying to find a simple general formulation of the backtracking problem. So, we have considered a path represented by S1, S2 to Si, and let T of S1, S2, Si be all possible values that Si plus 1 can take. So, we assume the existence of a bounding function Bi plus 1, a bounding function at step I plus 1, okay, expressed as predicates, such that if the function, if this bounding function Bi plus 1 is false for a given path at a particular node in the state space tree, if it is false for a path S1, S2 and so on up to Si, okay. So, if what we are trying to do here is, let us suppose we have already found or we have already traversed this path, okay, or we need to select a particular choice at the next node, okay. So, let us suppose one of the choices is S1, S2 and Si plus 1. But if the bounding function is not satisfied by that particular path from the root to that particular problem state, then the path cannot be extended to reach the answer node. We'll illustrate this in the next example. So let's consider this partial path S1 and S2. So let's suppose I here is equal to 2. So Si plus 1 is the choices that are available for Si plus 1 are 1, 4 and 6. Okay. So S1 and S2 is the current path that we have already explored. Okay. So for the time being, we have already explored 6 is one of the values in the solution in the partial vector, and 1 is the second one. Okay, second value in the partial vector. So T of 6 and 1 is 1, 4 and 6. So the possible values in the next state in Si here is 2, I here is 2. So Si plus 1 would be S3. Okay. So T of 6 comma 1 here is 1, 4 and 6. Okay. Let's suppose we choose 1 and verify whether this path can be followed or not. So we consider V3 of 6 comma 1 comma 1. Okay, and we try to test or find whether it is valid or not. But obviously when we reach this particular node here, okay, the score is 8. Okay, the score here is 8, and in order to win the match, it is important that at this stage the value or the score, the number of runs that needed to be made for these 3 balls here has to be greater than or equal to 13. Then only we can win the match or reach 18 or 20 runs. But it is obvious at this point here, if we follow this path, we select this node, okay, we will not be able to win the match, and none of the following nodes would yield us the solution. So we'll simply bound or stop expansion or searching for the tree here, and that is how we simply backtrack and select at this node. Since we find out that this red node here will not yield any solution if we follow all the other paths from this node, we'll simply backtrack and select some other node. Let's suppose this particular node, this particular possibility, and try to find a solution. So similarly, if we do this bound checking at each of these nodes while we are building this state space tree, then this is the tree that basically we will be able to get. This is a partial state space tree that will be yielded by backtracking. Okay, as I earlier said, this is not a standard problem. We will be discussing more standard problems in a couple of minutes. But this is just a simple example which helps you to understand what a state space tree is, how backtracking should somehow try to restrict the expansion of the possible states in order to find the solution, and restrict the partial state space or restrict the generation of the state space tree. Now, the general recursive algorithm for this backtracking problem is shown in the slide. It uses the same terminologies as we earlier discussed. So we'll go through this each of these statements one by one. For each k, okay, so here k means this k. This is a possible decision, this is a possible decision, and this is a possible decision. Okay, so k minus 1 is here, k minus 1. So k plus 1 meaning k here is either this option or this option or this option. So we try to exploit each of these options. So for each of the options available to us at the current node, okay, if the bounding function is satisfied, if the bounding function by choosing any particular k, so it means here, let's suppose we are at this node here, okay, for each possibility in the next step, okay, one of the possibilities is this, we need to verify the bounding function 6, 1 and 1, okay. If this will yield to an optimal solution, then we'll follow it. If it does not, then we'll simply backtrack and choose another node here or another option here, okay. So that is what this basically statement says. So if the bounding function satisfies the current choice, okay, and if this S1, S2, S3 and up to Sk is a path to the answer node, then we simply write that solution. Okay. Now, if we have not yet reached the answer node, okay, then we simply recursively make this backtrack call here for the next k. So if we have not exhausted all our moves, okay, if the solution is not complete yet, then we'll increment this k value in order to find the next step in the path. For example, in our earlier case, let's suppose if we had reached this point, okay, and we found that this is not feasible, okay, so we backtrack and choose this. The bounding functions tells us yes, you can proceed by considering this node, okay. So in case, since this is k minus 1, this is k, okay, and we'll simply increment k by considering the next decision. So this is k plus 1. So we'll treat this as the current node which needs expansion, okay, and we'll try to find all the possibilities that are available here. Another call to this backtrack function with k plus 1, so that will explore the possibilities of the current node, okay. So this obviously is a DFS algorithm, DFS meaning the depth first search algorithm, okay. You might implement breadth first search approach as well, because at the end of the day, backtracking basically simply tries to explore or traverse the state space tree, and it tries to optimize the search by restricting itself, by not expanding all possibilities, okay. So you can either explore the state space tree in a DFS fashion, in depth first search fashion, or in a breadth first search fashion. You can write a breadth first search algorithm yourself, and this algorithm, in this case, the recursive algorithm here is invoked by backtrack of 1, so starting from the first node, okay. Now we'll simply consider this one of the standard problems that is often used to illustrate backtracking, and this problem is known as 4 queens problem. Now, so what is this 4 queens problem? Basically, we are given a 4 cross 4 chessboard, and we are given 4 queens. We need to make our own choices as to where we need to place the queen, but the constraint here is that no 2 queens should be attacking. So 2 queens can be attacking if they belong to the same row. So for example, if you have placed a queen here, okay, you cannot place another queen in any of these boxes here, okay, places here. Similarly, you cannot place another queen in any of these 3 boxes either, because it is a common column. So here it is a common row, okay, so they belong to the same row. So 2 queens cannot belong to the same row, they cannot belong to the same column, and they cannot belong to the same diagonal, okay. So we cannot place another queen here. So if we have placed a queen in this box here, we can place another queen here, we can place another queen here compared to this one, okay. So obviously if we have placed another queen here, we cannot place the third queen in this box here, because it would be a common row for these 2 queens. Similarly, we cannot place another queen here because it would lie in the diagonal of this queen. Similarly, we cannot place it here, as it would be in the diagonal of this queen as well as in the common row of this queen. Similarly, we cannot place, and so on and so forth. So somehow we need to place these queens in such a way that they are not attacking. As I said, attacking here means that 2 queens are attacking if they are in the same column, if they are in the same row, or if they are in the same diagonal. So we need to find solution to this problem. A simplest backtracking solution to this problem would be, let's suppose we consider the first queen and place it in the first row and first column, okay. So the second queen cannot simply obviously be placed in the first row, because we have already placed one of the queens there. So it would be attacking if we place the second queen there. So we are again restricting our search in the state space tree. Otherwise, we could have placed, if we construct the state space tree for this problem here, the number of nodes in the state space tree, if we do not put any constraints, would be too many. So 4 raised power 4. Okay, so that is a large number of possibilities. So it would be difficult for us to search all those nodes or this large state space tree to find a solution. So let's suppose we have placed a queen in the top left corner. So the second queen, let's suppose we obviously cannot place them in the first column, because it would be attacking. Similarly, we cannot place it in the second column, for the second row I'm talking about, because otherwise it would again be attacking. So the only choice left to us, or one of the choices, not the only choice, one of the choices is the third column. Okay, so okay, the two queens that we have already placed are not attacking. So what about the third queen? So the third queen can be placed in the third row. We'll consider the third row for our solution in order to restrict the number of nodes in this state space tree. So again, if we look at the available options, the first column is not available because it would be attacking with the first queen. The second column is not available because it would be diagonally attacking the second queen. Okay, the third column is again not available because it would be attacking second queen in the column wise. Okay, so common column. Similarly, the fourth column is also not available. So what do we do here? So we simply correct a decision which has already been made, which we made earlier. Okay, by not proceeding with the current path, by simply restricting ourselves, stopping ourselves at this point of time, and then correcting a previous decision, trying to choose a different option. So we'll simply move our second queen to the fourth column there. Again, the two currently the two queens are not attacking. So the choice for the third queen is the first column is not available, the third column is not available because it will be diagonally attacking the second queen, and the fourth column is not available because again it would be attacking with the second queen. So the only available column in this case is the second column. Okay. Now what about the fourth queen now? Okay. So we cannot place it in the first column attacking with the first queen. We cannot place it in the second column. It would be attacking with the third queen. We cannot place it in the third column diagonally attacking with the third queen, and we cannot place in the fourth column. It would directly or column wise attacking the second queen. So again, we have to somehow modify our choices. Okay. Now we simply need to backtrack to the first decision. Because here we have already, we cannot proceed any further, and we have exhausted all the possibilities on the left side of the state space tree or one of the choices for queen number 1. Okay. So we need to alter our decision for queen number 1, and this is the result if we follow the same sequence. Okay. So this is one of the solutions, as you can see on the slide. So we have placed queen number 1 in the second column, then the first column for the second row and the second queen, the first column, the second column, the third column were not available, so we placed the second queen in the fourth column. Okay. Similarly, in the only place for the third queen was the first column, and the only place for the fourth queen was the third column, and this is one of the solutions, okay, for the 4 queens problem. And we'll see how using backtracking we were able to get this solution and how we were able to build the partial state space tree. So the solution vector to this problem is S1 is equal to 2. The first solution, first choice is 2, second choice is 4, third is 1, and the fourth one is 3. Or we can place the first queen in the second column, the second queen in the fourth column of the second row, the third queen in the first column of the third row, and the fourth queen in the third column of the fourth row. So we'll see how we build this solution. We'll try to find or construct the partial state space tree using backtracking, and please note that we are considering the depth first search algorithm, not the breadth first search algorithm for the time being. So we start from an empty root. Okay, the available choices to us for the first row are 4. Okay, 1, 2, 3, and 4. So we choose the first one. Okay, so we select and place the first queen in the first column of the first row. Now from this particular point, the second queen can, as I said, can not be placed directly in the same column. Okay, we see if we consider that case also, then our state space tree would have been very large. So we are simply omitting those cases where we have an option of placing a queen directly in one of the columns in which we have already placed a queen. So we are simply omitting that case. Okay. So the first column is not available to the second queen in the second row. So one of the choices is the second, for example, column. Okay. But when we place it and we try to find using our binding function whether this move is valid or not, we'll see that they are diagonally attacking. Okay. So we'll stop growing this solution here. As you can see, we have marked this node as red. It simply means that we will not be proceeding any further or following any other paths from this subpath. Okay, and we'll simply backtrack and choose a different column for the second queen. So we have chosen column number 3 for this second queen. Okay, so are the two attacking? No, they are not attacking, so we can proceed further. Okay, so at this point of time, for the third queen in the third row, we have an option. Again, in the first column we cannot place it, okay, because that has already been occupied by the first queen. The second column is free, okay, and we'll simply place this third queen in the second column, okay, of the second row. So we have to check our bounding functions and see whether this currently placed queen is attacking any of the queens that have already been placed. And as we can see, they are the second queen and the first queen are attacking. So this solution is not feasible. So we cannot proceed any further using this solution. So we'll simply bind it. Okay, we'll stop it there and try to choose an alternative column for third queen. Again, we have omitted the use of third column for the third row because that has already been occupied by the second queen. So the third column has already been occupied by the second queen. So we are not considering that case. So the second free column for the third queen here is the fourth column. Okay, so we choose that and find out that none of the queens is it attacking? Yes, the third queen is attacking the second queen. So we cannot use this particular solution and we'll simply bind this path here. So we'll mark it red and try to correct our decisions that we made before. So we'll try to place queen number 2 in the fourth column. Okay, so this was the third choice available at row number 2. Okay, so we have placed queen number 2 in column number 4 and try to see whether this will yield a solution or not. So in the third row for this case here, one of the free columns is column number 2. Okay, or is this particular queen attacking with any of the two queens that we have already placed? No, it is not. So this is one of the possible paths that we can expand or explore in order to find the final solution. So in the fourth queen, in the fourth row, the only free column is the third column. And we simply place this queen there and then try to find using the binding function whether this was a valid move or not. And we see that the fourth queen is attacking the third queen, and we simply mark it as red and we will not proceed any further. Now, if you look at this partial subtree here, we have exhausted all possible moves considering the fact when we placed queen number 1, okay, in column number 1 in the first row. So okay, these were so we have exhausted all the moves in that case. So we find that queen number 4 attacks queen number 3. Okay, so we'll simply bind this path and try to find an alternative path by making a different selection at row number for queen number 3 or row number 3. So the second option that was available at row number 3 or queen number 3 was that we place queen number 3 at column number 3. So we select that option and place the queen there, and we find that it is simply attacking the second queen. So again, this option is not valid and will not proceed any further or search other solutions. So at this point of time, we can see that we have exhausted all possible moves for the case when we place queen number 1 in column number 1 for row number 1. Okay, so we do not have any other move left in case of placing queen number 1 in row number 1. So we simply make an alternative choice. So we explore the possibility that we place queen number 1 in column number 2, okay, and then try to find a solution. So for the second queen now, once we have placed queen number 1 in column number 1 for the first row, in the second row, the first column that is free is the first one and we place the queen there, second queen there. But later on we find by bound testing that the move is not feasible, okay, so we remove this queen and bind the solution. Okay, so the next free column for the second row for the second queen is column number 3. So we place the queen there, and then again by bound testing we find that the move is not valid because they are attacking diagonally. So we stop exploring other possibilities using this sub path, and we place the queen in the next available free column, that is column number 4 for the second row, and we find out that the currently placed queens are not attacking. So it is a possible sub path that can be explored further. So for the third queen, the first free column is the first one. Okay, so we select this particular column and place the queen there, and then by bound testing we find that none of the queens so far that have been placed are attacking. Okay, and we finally proceed with this path, proceed exploring this path. As I said, we are following a depth first search algorithm here. So for the fourth queen, the only free column available is column number 3, and we place our queen there. Okay, and by the end of this node we find that all our queens have been placed and none of them is attacking, and this path here now, it means this solution vector here, meaning we select column number 2 for the first row or the first queen, then we select column number 4 for the second queen, second row, then we select column number 1 for the third queen, third row, and finally we select column number 3 for the fourth queen, that is in the fourth row, and this vector or 2, 4, 1, 3 is the final solution vector. So this is just an example of using backtracking. You can simply see the red nodes at the red nodes. If had we not used the bounding function, then we'd have to search all the subtrees that were following these red nodes over there. But by using backtracking, we restrict ourselves to only a certain partial subtree or in the state space tree which needs to be explored for finding the solution. In the next class, we will be discussing a more generalized algorithm for this 4 queens problem. We will consider the n queens problem and try to find a generalized solution using backtracking for the n queens problem. Till then, thank you.